Okay, so it's welcome everybody to this week's Majorana-Raychaudhuri seminar series. It's a pleasure to have Professor Subir Sarkar from Oxford as this week's lecturer, and he's going to talk about ruling out light axions. The writing is on the wall.
Well, thank you very much for the invitation. I have in fact spoken in your series before. I think when you started it, was it 2 or 3 years ago, right? During the lockdown. And
2 years
I'm
ago.
happy to see
Two
that
years.
you have thrived and in fact have gained a large audience and are now putting videos on YouTube. That certainly is quite helpful because one can go back and look at some of the talks. Um, so today, I want to talk about a problem that has been discussed for nearly 40 years now, as you will see. But in fact, there is a new twist in it, which we only discovered recently. And this work has been done with my ex-student, Konstantin Bayer, who is now a postdoc at Max Planck Institute for Kernphysik in Heidelberg. And it has, in fact, motivated a new experiment, which was done at the X-ray free electron laser in Hamburg. This was led by my laser colleague, Gianluca Gregory, and I'll talk about that towards the end. So the abstract is up here. The background is a simulation of a domain wall network in Axions, but I'll explain all when it comes to discussing the evolution of this system. So let me actually begin by telling you a bit about this journal, SciPost Physics, in which this paper was published, because I think not everyone knows about this. And I want to assert that most of us are pretty stressed about the nature of academic publishing these days. We all know that many scientific journals are just profit-making ventures and exploiters. So our condensed matter theory colleagues took an initiative to start a new journal, which, as it says here, is published by physicists for physicists. And our paper appeared there. And what I want to highlight for you is that in contrast to all other journals I know of, the submissions and reports, the referee reports and the responses, it's all public on the web page. The referees can choose to remain anonymous if they want to. But it is very helpful to have all these referee reports and the author's response publicly available, because I'm sure that many of us have had the experience of having a paper, objected to or even rejected by a hostile referee. And the whole business is just between you and the referee and the editor, and nobody else gets to hear about it. So we call this peer witnessed review. And this is something that is unique in scientific publishing, as far as we know. And the advantage, of course, is obvious. If you really have a strong case for publication, it is, there for the whole world to see. And moreover, apart from the referees, anyone can comment on your paper. They can post a public comment there if they find a, problem with equation 4.2. They can tell you so, etc. And because of this, and because it also is something that you can directly send papers to from the archive, it's actually very cheap to publish. And we are therefore able to offer it free to both readers and contributors. That's called diamond open access in the current jargon. And the funding basically comes from asking the institutions of the authors to pay a very modest sum. It costs about 150 euro per paper. And those of you who have paid so-called open access charges would know that it typically costs 10 times more than that. So I would say to all of you, if you get requests for refereeing from SciPost, please accept, because this thing only works because we give our time and effort to support this non-profit enterprise. And can I suggest that it is more worth your while doing it for a journal that is not trying to make money off you, but is there for the community's benefit? Okay, so that was the plug for this journal, which was started by a colleague, Jean-Sébastien Coe, who is now at the University of Amsterdam. And I'm happy to say that it has actually now got a citation impact rivaling that of much better known journals earlier. So as for the topic of this seminar, it's basically about dark matter. And we know from this impressionistic sort of picture by Tim Tate, the landscape of dark matter candidates is quite broad. I hope Tim gets 10 cents for every time somebody shows this picture. You'd be rich by now. But basically, there are two classes of particles here, weakly interacting massive particles, and at the left-hand corner, there are axions. So in fact, both were proposed in the mid-80s, and the searches for them began in the mid-80s. But WIMPs, of course, had the priority because they were clear signatures of new physics at the electroweak scale, whether supersymmetry or extra dimensions or technicolor and so on. And those are all in the upper right-hand corner of this picture. Axions were proposed around the same time, but they did not attract as much attention. And in the last 10 years or so, the situation has reversed because of our failure to find WIMPs, to put it bluntly. Now, I'm going to focus on QCD axions, but they are, of course, a subclass of a broader category of dark matter candidates, bosonic dark matter, which includes both scalars and pseudoscalars like the axion, and also vectors, like dark photons and so forth. And there is a nice review there I've pointed out for those who like to more about this class of dark matter particles. So why QCD axions? Well, because it is motivated by an issue in the standard model itself, which we all know and love. And we know that at the renormalizable level in the standard model, the Lagrangian is missing a term, apart from the familiar, the gauge forces and the fermions and the Higgs. There is also the freedom to add a term, which is boxed in there, which is perfectly natural. It's perfectly well allowed by all the symmetries we know. However, it would lead to CP violation in the strong interactions. And a very interesting calculation shows how this term would give rise to an electric dipole moment for neutrons. This is something that experimentalists have taken up as a challenge. And although the measurements are difficult, they have been able to set an extremely tight upper limit on this quantity, which then implies that this theta QCD parameter is less than 1 part in 10 to the 10. And this is, in fact, the sum of both the actual theta QCD that enters into the CP violation for the dipole moment for neutrons, has a contribution also from the quark mass matrix where there is CP violation. So it's a bare term plus the argument of the determinant of the quark mass matrix. And it is that fine tuning, which must be exact to 1 part in 10 to the 10, which is problematic. And, we cannot possibly accept that it is something that can happen unless there is some symmetry giving rise to it. And that is why the proposal by Peche and Quinn to make this a dynamical parameter so that it has a potential, it relaxes to zero dynamically, was so well received. And soon after, as you all know, Weinberg and Wilczek pointed out that this spontaneous violation of this Peche-Quinn symmetry would give you a Nambu-Goldstone boson, much as the breaking of chiral symmetry by the quark condensate in at the QCD scale generates the pion. And indeed, the axion is closely related to the pion, the two mix together. And so many of the axion properties can be scaled relative to the pion properties in ratio to their decay constants. And much effort has gone into calculating the mass of the axion on the lattice. And the value that I've quoted there is from a recent calculation taking into account many subtle effects. So basically, had this FA been at the electroweak scale, as was first believed, the axion would have been of order MeV in mass, and people searched for it at CERN. And some of you may not know that it was even found. It was called the Axion, and that gives you a clue as to which group found it. But of course, it turned out to be some experimental background, neutron punch-through. There are no axions associated with the electric weak scale, and it had to be, FA had to be higher. And then people said, well, FA could be very high and axion could effectively decouple from the standard model, and you'll never find it. And so everybody is happy. However, then theorists realized that actually, even if the axion was extremely weakly coupled and did not really matter in laboratory experiments at CERN, it would in fact have a huge impact on early universe cosmology, because the mixing with the pion gives the axion a potential, a mass, and it would oscillate about its minimum, as is indicated here, once that potential develops. But because it doesn't interact with matter, it doesn't dissipate, and therefore it keeps oscillating. And these coherent oscillations of the axion field across the entire universe, they are amazing oscillations. They don't carry any net momentum. They average out to zero. These oscillations carry energy density. And if you look at the equation of state, it's exactly the same as that of non-relativistic particles. So in fact, they act exactly as cold dark matter would. And therefore, since that was something that was being demanded from considerations of structure formation in cosmology, this was just what the doctor ordered. And it was realized that this FA, in order not to overproduce dark matter, had to be less than 10 to the 12 GeV. But at the same time, if it was less than 10 to the 10 GeV, then axions would interact sufficiently strongly with matter that they would carry energy out from stars, where they would be created by the Primakov process. And by constraining energy loss from red giants and so forth, you could then say that F had to be higher than 10 to the 10 GeV. And that gives you this light axion mass window, microelectron volt to 100 microelectron volt, which has been the focus of attention for most of the last 40 years. However, this simple argument, or actually not simple, but a very elegant argument, I would say, has not accounted for the fact that axions contribute to dark matter not simply through the coherent oscillations, the misalignment mechanism, but also from the formation of topological defects in the axion field. Because, as you know, when a symmetry breaks to a lesser one, if you look at the quotient group, the homotopy of that determines if there are topological defects that can form in the manifold. And axions can support both strings and domain walls. So first, let us remind ourselves of this nice argument for coherent oscillations, which was published by these groups of authors, Preskill, Wise, and Wilczek, then Larry Abbott and Pierre Sikivi, and Mike Dine and Willy Fischler. Notice that they're all in the same issue of Physics Letters, because the editor insisted that they should appear together in order that all these people together are credited appropriately. So those days, the editors of journals actually took responsibilities like this seriously. Now, the oscillations are familiar to you. So the point is, of course, the axion could start out at the minimum of the potential, but that would be fine-tuned. Naturally, it would be a radian away from the minimum, and that is what is usually assumed in calculating the energy density in the oscillations. And of course, you could always argue for some anthropic selection of that angle so that the energy density is as small as you want it to be, but we will not discuss anthropic arguments here. Now, the argument for FA being restricted is as indicated here. As I said, FA is restricted from above by the requirement that dark matter should not be overproduced, and from below by stellar evolution. And the axion window that I referred to is that little gap there. And laboratory researches have mainly been focused on this region, because that was what was indicated by the early arguments. Now, there is a twist to this whole business, which is that it depends on whether the Pechak-Quinn symmetry breaks before or after inflation. So if it breaks before inflation, then obviously one little patch of space-time, where the axion field is whatever it is blown up to be our entire universe today. But if Pechogian symmetry breaks after inflation, then it breaks differently at different points in space-time, which are outside each other's causal horizon at the time, and later come within the common particle horizon. And at that point, topological defects can form in the field. So the problem that I'll discuss is entirely restricted to the post-inflationary scenario. It is not a problem for the pre-inflationary scenario. I want to make that very clear. However, whereas inflation was generally considered to have happened at the granulated scale for a long time, and indeed it still could be there because the upper bound on the inflationary scale from the absence of gravitational wave background is at about 10 to the 16 GeV. However, we have come to realize that inflation can essentially happen at any scale down to the electroweak scale. You don't want it to happen below the electric scale because you want to make baryons after all. And so, but that still gives you 14 orders of magnitude in energy where you could have inflation. And there is no reason for it to be up at the gut scale. And there are plenty of arguments for low scale inflation, which are being revived these days. So I think that this post-inflationary scenario is worth taking seriously. Now, when you look at the arguments that have been placed on axions, it is now customary to do it as is shown here in the plane of the axion photon coupling, which is common to any kind of axion. Just like the pion couples to two photons through the triangle anomaly, so does the axion. And that coupling is plotted here against the axion mass. You could put the axion Pechogian scale on the top x-axis because just the inverse of the mass. And this diagonal band that you see here is, of course, the relation between the coupling and the mass in specific models. The two models that are shown here came, so I'll discuss this in the next slide. K is VZ and DF as Z. They kind of bracket the range of possibilities. In fact, they are obtained subject to certain restrictive conditions. So more recently, there has been interesting work by my colleague Pratik Agrawal and others, opening up this window and suggesting that you could have a much broader class of axion models which don't necessarily have to lie on that band, and that would actually have implications for grand unification as well. But let us, for the moment, stick to this picture. So what you see here is that the astrophysical bounds that I talked about, the energy loss from globular clusters, sun, supernova 87A, etc., they are all like horizontal lines on this. They require the axion photon coupling to be less than something. And then there are many, many arguments from early universe physics, Big Bang nucleosynthesis, cosmic microwave background, spectral distortions, extragalactic background light, etc., which are relevant for heavier axions. But for the axion, light axion window, which I referred to earlier, that's where most of the microwave cavity experiments are. And they probe down to a level which is dependent on what they assume for the local density of axions. And if you consider that axions make up all the halo dark matter, which they optimistically take to be 0.45 GeV per cubic centimeter, then you will get these vertical bands that you see here from various experiments. And you can see that they're actually now reaching the expected sensitivity, the required sensitivity to prove for axions. So things are quite exciting. In fact, just a month ago, there was a rumor that ADMX might have seen something. So, people are on tenterhooks about this. Now, the experiment, these experiments essentially exploit the axion to two photon coupling. So one photon is a virtual photon that is provided by a large magnet, and a passing axion can then convert that into a real photon, and via that coupling I mentioned. And these experiments have reached pretty high levels of sophistication. So on the left, you have the ADMX experiment, and on the right-hand side, you have the haystack experiment, which uses novel quantum sensors, and that is now the new game in town to improve the process by which you scan a cavity for the axion line, which is very tedious because, as you can see, delta mu by nu is 10 to the minus 6. It's an extremely narrow line. It's like you're trying to tune a old-fashioned radio, trying to catch a station. And if you just turn the knob a little too quickly, you'll just skim over it. You won't see it. And unfortunately, the time taken to achieve a certain amount of signal to noise goes as the square. And so basically, it takes a long time to get a sensitive measurement if you really want to scan that parameter space very carefully. So people are trying to figure out ways to do this in a in a faster manner. But they have nevertheless made significant and impressive inroads into the parameter space here. And there are initiatives, as you may know, all over the world, in Florida, in Washington, in Yale, and so on, so on. And new experiments are being motivated all the time here. But the question that I would ask somewhat provocatively here is, are they in fact looking in the right place? Because that Axion window was motivated, I remind you, by the misalignment mechanism for the relic Axion abundance. So let's take a minute to look at this couplings for Axions. So as I said, all Axions have this coupling to two photons, this kind of universal coupling. It does matter what the model is, but as you can see here, it's almost the same for the KSVZ and the DFSZ model, is factor of 3. However, you can have very model-dependent couplings to fermions. So you might actually have axion that couples only to, it doesn't couple to leptons at all. So it could be a hydrophobic axion. And that would be a model that was presented by Kim, Schiffman, Weinstein, and Zakharov, KSVZ. So they introduced basically one super heavy quark, which carries Pechequin charge. And the alternative was proposed by Dine, Fischler, Shrednicki, and Zhitnitsky. So these three authors wrote the first paper, and Zhitnitsky wrote it separately, but again, they appeared in the same issue of Physics Letters. And here you have a scalar field which carries Pechequin charge. So any fermion that couples to it picks it up. And the number of particles, quarks, that are charged under this Pechequin charge, we call NDW, okay, for a reason that will become clear. That's what actually determines if you're going to form domain walls or not. Now, this KSVZ axion doesn't interact with leptons, only with quarks, whereas the DFSZ axion interacts with both leptons and quarks, and in that sense is more generic. Now, in the early universe, after Pechequin symmetry breaking, the manifold is not simply connected, and you can form cosmic strings always. But when the temperature drops down to TQCT, then you can break the symmetry further to a discrete symmetry, Z, with the argument is the number NDW, this number that I have given here. So for example, for DFSZ, NDW is 6. And that would give rise to the creation of domain walls. Now, strings are sort of quite well known and have been discussed for a long time, not just by particle physicists, but also in condensed matter physics. They in fact are seen. They are actual real objects you can see in liquid helium, for example. And these are non-contractible loops in the manifold, the vacuum manifold here that we're talking about. So we're talking about a relativistic version of what condensed matter people do. And strings can be modeled on a lattice, the formation of strings and their evolution. They form an intricate, complex network, and small strings, loops decay typically into the particles that they're made of, which in this case are axions, because remember, the core of the string is the original vacuum, the symmetric vacuum. And strings are actually amazing objects. If you go around them, there is a chunk of space-time missing, proportional to g times mu, where mu is the string tension. And typically in a cosmological simulation, we find that there are something of between 1 and 1,000 strings per Hubble volume, but the only scale in the problem is the Hubble radius. So typically you would only get structure on that scale in the cosmic string network. Now, I could spend a whole hour just talking about how these simulations are done, but my focus is elsewhere. So I'll just refer to this recent study by a group from based at Berkeley, who did a very elaborate simulation of cosmic string networks on a huge lattice, zillions of particles, and everything is in color, so you should believe all this. And they can, in fact, resolve all kinds of details about the simulation, the radiation from the strings, and their intercutting, etc., etc. And the bottom line of this work is that the string network radiates about 25% more axions than the energy density that was there in the coherent oscillations. So they say that the preferred mass range is no longer what I mentioned earlier. It is now a bit higher. It is between 40 and 180 microelectron volts. They're very definite about it. And they even say that this is higher than what is being proved by the two main dedicated experiments, which I mentioned, ADMX and Haystack. So this is, of course, interesting. They are not the only people doing this. There is also interesting work being done by Ed Hardy and collaborators, by Kiran O'Hare and collaborators, and Japanese group Saikawa and so on. And they don't all agree in detail, but broadly they agree that the strings, axions radiated by the string network contribute more dark matter, which needs to be taken into account. So they quote slightly different mass ranges for the axions. The point I want to make is that experimentalists are paying attention to these arguments. And for example, the calculation by Bushman et al. Motivated a new experiment, a plasma haloscope, which in fact is currently being set up and soon going to take data. And as you see here, as the caption here says, they are focusing on this Bushman et al. Prediction of where the axion mass should be, taking into account the extra axions radiated by the string network. And they are going to use a new experimental technique in order to look for these axions. Actually, I think the truth is that the new experimental technique is itself very interesting, and this has provided a good physics motivation for it. As my friend Rocky Kolb likes to say, to the man with a hammer, the world looks like a nail, right? So if you are an experimentalist and you have a good method, then you look for something that you can use it on. But, we hope that they will be successful. But the bottom line is that this new region that they're focusing on, which they've highlighted here, is certainly taking into account a second contribution to the dark matter from the axions radiated by strings, but it has ignored another contribution, the domain walls, which also form in the post-inflation scenario. Now, the domain walls, as I mentioned, form only when the temperature cools to around the QCD scale and the quark condensate forms. The instantons in QCD have a very steep temperature dependence, so it turns on very quickly below about a GeV. And at that point, the axion gets a mass through its mixing with the pion and develops a potential. The Mexican hat tilts, and then you have oscillations around that. But that manifold that you're seeing there will be corrugated. I'll show it in the next slide. And it will have n dW discrete vacua, and the domain walls form at those boundaries. They are typically bounded by strings. So you get a complex network of domain walls linked to strings. And all this is happening at around 10 microseconds after the Big Bang. Now, the energy density of these walls is scaling as 1 over T, as opposed to that of matter or radiation that scales as T square. So you can see that they will come to dominate. And Sikivi realized this back in 1982 and said, well, the domain wall network has to collapse before they come to dominate. We should be at something like around nucleosynthesis time for a typical value of F Pechequin. And the reason why they need to collapse is because if the domain walls come to dominate, then you can easily see that they will actually start inflating the universe, not exponentially, but as a power law, right? But nevertheless, inflation. You might think, what's wrong with that? We could do with a mechanism for inflation. The problem is that this inflation will never end. So right from the QCD scale, the universe goes into, eternal inflation, and we never get a hot Big Bang. That, of course, is not the universe we live in, and therefore this is a problem. This is a serious problem that is, in fact, relevant to any particle physics model with a discrete symmetry. And this was first recognized in this seminal paper by Yakov Zeldovich, Kubzarev, and Okun. They were, in fact, considering discrete CP, but their argument holds exactly the same for Pecek-Quinn symmetry. And as they say in this paper published in JETP, if there is no mechanism that leads to the disappearance of domains at a sufficiently early stage of the evolution of the universe, it would lead to conclusions which are in contradiction with experiment. And in other words, there will be no universe. So quite understated. Now, Pear has actually spent most of his career working on axions, and he recognized that this was a problem for axion cosmology. But he also suggested a solution back in 82. He said, why don't we break that Zn symmetry, the discrete symmetry, slightly, not so much badly that it will upset the Pecek-Quinn mechanism, but enough that the domain walls will disappear a certain time after their formation. And that is a good idea, but we'll have to see if it actually can work in practice. Because once the domain walls collapse, the energy that is contained in them will be radiated. Now, the domain walls are basically made of axions, so they will radiate a lot of axions. And because they also have, in principle, high tension, they will radiate gravitational waves. So these are the two ways that you can get rid of, that domain walls can radiate. However, Michael Dine, who has thought about this, thinks that this is not a problem. Okay, so this is from a talk that he gave at a meeting we had in the Galileo Institute in Florence last year. And he says, my claim is that provided there are symmetry violating effects that eliminate the domain walls before they dominate the energy density, these will collapse, and most of their energy is converted to kinetic energy of the walls, which in turn converted to extremely relativistic axions, which don't contribute significantly to the I think he means dark matter budget. So basically saying that the axions that are created are so relativistic that they will just redshift like radiation after that, and it won't be a problem. Of course, they will contribute to the radiation bath, and these days you might worry about the limit on the number of, N effective, which you have a tight bound on from CMB and nucleosynthesis, but, you could perhaps get away with that. And subsequently, Dine and collaborators have written a paper arguing for this. However, we thought you would examine this argument. This was not a quantitative argument, just his belief. So we thought you would actually work out the evolution and collapse of the domain wall network and see how much these radiated axions actually contribute to the dark matter abundance. Largely because some years ago I had actually worked on domain wall network evolution. So I looked at the literature, and I found to my surprise that although this issue has been widely discussed, so here, for example, is a white paper with many, many authors that was presented to the snowmass exercise, and they say that indeed this phenomenology of draying strings, domain walls, etc., has been studied extensively, but no consensus has been reached regarding the relevance of their contribution. And another white paper on wave dark matter, which light axions would be, says there is insufficient understanding of the production that receives possibly significant contributions. So obviously, this is something worth looking at. And actually, I might say as an aside, I was a bit surprised because there have been hundreds of papers on this. And so, you might think that it has all been sorted. But I would say this for the, early career researchers in the audience, it's always worth looking at the literature, even if it looks like everything has been done. Even in a well-plowed field, sometimes there is a interesting result that has been overlooked. So let's look more carefully at the formation of the domain walls. As I advertised earlier, that manifold the Mexican hat button that is corrugated, there are NW minima, and the domain walls form at those junctions, bounded by cosmic strings, as I mentioned. You can calculate the profile of a domain wall by solving the equation of motion. This is, for example, from a paper where we studied domain walls in the next to minimal supersymmetric standard model. I'll refer to it a minute later. And the argument has been that if NW is 1, then the string wall network disappears. Although there is a recent paper which I would point you to, a very interesting paper, which says that this may not be the case even for NW equal to 1. But certainly it is generally accepted that for NW more than 1, for example, the DFSC model of Axions, the domain wall network survives. And you can see just visually, this is a picture from a paper by Sekivi and collaborators. If you have a Z3 symmetry, so I just mark a honeycomb randomly with 1, 2, and 3, and then I can you see, identify regions where there are the same sign vacuum, and then here this is a different sign vacuum, and the things at the boundary of the domain walls. So Sekivi and collaborators did one of the first simulations of this. You can see here that the scale of this picture here is many, many times the Hubble radius. So typically there is order of 1 wall per Hubble volume. These things are whipping around at the speed of light. And remember that in their code, they still have the regional unrestored, the symmetric vacuum before pressure symmetry breaking. So these are amazing relativistic objects. They have very interesting gravitational properties, but we don't have time to go into all that here. Let's just look at how you do these simulations in a very general sense. So this is something that we have to tackle when I set my student Sebastian Larsen to solve this problem. And basically, you write down the semi-classical equation of motion for a scalar field with some potential, which you can take to be some kind of a Mexican hat potential as here. And typically, you write it in conformal time, which is usual time divided by the scale factor to take that out. But the result of that is that you get a factor of a square on the right-hand side of this equation. And this is a problem numerically, because as you see, as A increases as time goes on in your cosmological simulation, this barrier is getting higher and higher. And that means that the wall solution, which I showed in the previous slide, gets increasingly narrower in co-moving coordinates. So it's very hard to model this on a lattice, on a grid. Now, the solution to this was suggested as a numerical trick by Bill Press and collaborators. And they said, why don't you just generalize this equation of motion so that instead of this 2 here and this 2 here, you call them alpha and beta and choose beta equal to 0. In other words, this barrier does not change in height as evolution goes on. And you take alpha equal to 3 in order to ensure that momentum is conserved, because that's something we can't afford to violate. And in fact, we found that this suggestion was a very good one. When we did the simulation, we found that the results are very similar to what you get for alpha equal to beta equal to 2, which is the real situation, which we can do over a very limited range of conformal time. But we get agreement with that with this numerical trick. Now, these days, we used a 128 GUB grid. Today's simulations are being done with grids which are 1,000 times bigger, sort of billion times larger. But the basic argument was to determine how the wall network area scales. And in fact, we found it goes roughly as 1 over eta. Eta equal to minus nu. Nu we found to be 0.92 plus minus 0.08, pretty close to 1. And that is actually what Tom Kibble had already said it was from a very elegant analytic argument, which is called Kibble scaling. And in fact, at the same time that we are doing this work, which was in 1996 and published it in 97, this is with, as I said, Sebastian Larsen and Peter White. Mark Hindmarsh, who was then in Sussex, was in fact looking at a non-relativistic model, which the condensed matter people use to describe topological defect dynamics in their systems, liquid helium and so on. And he managed to generalize it to the relativistic case, and that also gave this result. So we kind of supported each other and convinced each other that we must both be right. Now, going back to the particle physics as to why that breaking of that Zn symmetry must occur, that argument actually came 10 years later after Pierre Sekivi motivated that it had to be there. And this was the realization by Kamionkowski and John Marsh Russell, my colleague, and Holman et al., and also Dave Seckel and Barr, that global symmetries are generically violated by quantum gravity. And so you can, without actually having a theory of quantum gravity, you can't, of course, calculate these. But generically, in an effective field theory approach, you can always write down a non-renormalizable operator, as here, which would violate any global symmetry that you can think of. In this case, you're talking about Peche-Quinn symmetry. And this would mean that you would introduce a tilt in the potential so that, that flat potential would get a slight preference for one vacuum over others. And that tilt would be given to related to the order of this operator as given by this expression here. Now, this G prefactor and also this phase delta, these are also things that should really come out of some ultraviolet, some quantum gravity theory, which we don't have. So you could argue that they don't have to be one. For example, if this is being done by wormholes or something, then it could be quite a lot smaller. But typically, you would expect them to be of order 1, and even if you fine-tune them, you would not really want to fine-tune them more than, say, 1 part in 100. We'll come back to that later. So we did our numerical simulations for a generic tilt, and also something we call bias, which is the possibility that one vacuum gets preferred over others, because the field in which the symmetry breaking is occurring could be light compared to the Hubble parameter during inflation, in which case it will do a random walk during inflation. It will take a step of order the Hubble parameter every Hubble time, and the random walk means that it will get away from the minimum by square root of the number of steps. So at the end of inflation, it may not actually be where you think it is for a strongly coupled field. And so Horacio Cassini and I looked at this and worked out what bias should be created for a given weak coupling field and for a certain scale of inflation. However, it turns out that is not relevant for axions because the step size here is much, much smaller than the field excursion that we are concerned with, which is the Peche-Quinn scale. So I won't discuss that further. I'm only going to discuss tilt, which is the case being referred to here. So as you can see here, the wall network reaches that scaling regime I mentioned, going as 1 over eta. But when this tilt is turned on, at some point, as this particle horizon is increasing and different domains are coming within it, it'll turn out that statistically they are more likely to be the same sign than different signs. And at that point, the wall network suddenly finds it has no support and it will collapse exponentially. And Sebastian's simulations were good enough to even show some dynamics of that collapse. You can see that it is radiating off the Nambu-Goldstone bosons of the underlying spontaneously broken symmetry. These are these little wiggles that you see here. And actually, you can do these simulations even in Mathematica. Here is one that Steve Abel did when we looked at the next to minimal supersymmetric standard model, which has a Z3 symmetry, in order to try to solve the notorious mu problem of the MSSM. And by introducing a scalar, a singlet Higgs, you can solve the mu problem, bring it down, explain why it is at the electric scale and not at a high scale. But that gives you domain walls made out of Higgses, which then would collapse at the electroweak scale. Otherwise, they would come to dominate the universe. And that, in order to create the tilt to make them disappear, you have to violate the Z3 symmetry, and that resuscitates the mu problem. So in that paper, we showed that you can't really have the NMSSM, and you have to do something about the Z3 symmetry. Maybe you have to embed it in a continuous symmetry and so on. And it's basically the same kind of argument you're making here. You want to violate the discrete symmetry in the DSVZ model, but you can't violate it too badly because that will then resuscitate the neutron dipole moment. So that is basically the issue. We have a constraint from a cosmological requirement, but you have an opposing constraint from laboratory experimental physics. And that is a good situation to be in because the answer has to be in between them. It has to satisfy them both. So when we actually quantify this argument, and this is, you will find that in the paper by Konstantin and myself, we find that the order of the discrete symmetry, which of course has to be something integer. So we have marked the values of the Pechukin scale at the integral values of this order of the non-renormalizable operator. And you can see that this is kind of illustrating what is called the quality problem for the axion. You would need to suppress a lot of operators if you of allowed higher dimension operators if you want to protect the axion. And typically, you would have a better life if you actually made Pechukin scale quite low, not as high as people think it ought to be in order to avoid stellar constraints. And I mentioned that you could fine-tune that prefactor G and delta, but even if you fine-tune them, say by 1 by 100, you don't actually change the conclusion that much. Now, 15 to 20 years later, that early work was forgotten, as it often is, and people started doing new simulations of domain wall networks, which are far more sophisticated. And now the pictures are in color. And you can now see lots of interesting detail in the simulations. You can calculate the spectrum of axions, which actually, again, Sikivi and Harari had said would be a power law, as is seen here. But the point is that now we can actually read off from the simulations specific numbers like what is the typical momentum of the axions that are produced by wall decay. Turns out in the first simulations, it was something like 100, but now the answer is closer to something like 5. And this is what is the counter to the belief of Mike Dine that the walls radiate extremely relativistic axions. The simulations do not support that intuition. So basically, we can now just look at the simple argument as to what happens to the energy density in the walls. And what is plotted here is the energy density as a fraction of the ratio to the critical energy density versus the time in units of the inverse mass of the axion, just so that you can get it all on one plot. And you have chosen some particular values for the stilt parameter and for the Pechukin scale. And what is shown here is the energy density in the walls, which as you see here is scaling as 1 over T, the brown line. And then at some point, the tilt is enough to make the wall network collapse, and it collapses exponentially. But when it collapses, the energy density doesn't just disappear. It goes into relativistic axions, which then follow this green line. The green line is steeper because relativistic particles are redshifting, in contrast to the dark matter in the universe, which is this brown line here. And basically, we have to see that this green line it goes down to the point where the axions become non-relativistic, and then they also become dark matter. But that dark matter cannot exceed this brown line. So this green line had better meet the brown line and stay behind it. This is the limiting case, right? So the constraint is effectively coming from the fact that the domain wall decay must happen early enough to allow the decay axions from the wall network to redshift sufficiently before they become non-relativistic and contribute to the dark matter. and that contribution should not exceed the amount of dark matter we know there is in the universe. Okay, it's a very simple argument illustrated in this cartoon here. For reference, I'm also showing you the radiation background of the universe. This is all happening in the radiation-dominated era. And we also calculated the radiation of gravitational waves from the wall network in the usual quadrupolar approximation. That is shown as this blue line. It is totally subdominant and is unimportant compared to the radiation of axions. The simulations that I referred to by the Japanese group are more sophisticated, and they obtain an answer which is a few times larger than we have here. But you can see there are orders of magnitude, so it doesn't change the conclusion. So the bottom line is that the walls must decay very soon after they're born in order that the relic abundance does not exceed that of dark matter. And you can see this all on this plot of the Pechequin scale versus the tilt parameter. The tilt parameter cannot be too large, otherwise you resuscitate the neutron electric dipole moment, which is restricted to make theta less than 10 to the minus 10. But on this side, if mu is too small, then the walls survive far too long, and that would then be cosmologically unacceptable. If I take the axions from the wall to be fairly relativistic, with a ratio of energy to mass of around 100, then you get this exclusion line, which is marked here. If I take them to be 5, which is what the more recent simulations are suggesting, then you would rule out this band as well. Okay. And therefore, the numbers we are quoting are very conservative. You can see from the conservative plot here that the axion mass is now being restricted at the limit, which is acceptable, to be more than 11 millielectron volts. And that corresponds to a Pechequin, bound on the Pechequin scale, of about 5 times 10 to the 8 GeV, if you read it off from here. Now, of course, we are assuming that axions make up all the dark matter, which is also very conservative. In principle, there could be other contributions, so that we parameterize by fraction XA. So you take for that whatever number you like. Now, studies of structure formation with axions which were initially relativistic when they were created and then turned non-relativistic, this has not been done to my knowledge. People normally talk about axions being cool dark matter right from the go, or we know what happens with hot dark matter, but not this intermediate case. So now if you look at that plot that I showed earlier, we are no longer here in the axion window. We have to be to the right of this line, and this really is a game changer. We must look for axions in the mass range more than 10 millielectron volts. And there are not that many experiments there. There's only this light shining through walls experiment at DAISY, and there is a proposal for EAXO, which is an International Axion Observatory, the successor to the CAST experiment that was at CERN and was using an old magnet to look at the sun through to see if any axions from the sun convert into X-ray photons. So I'm running out of time, so I'll speed up a bit. Here is a picture from Ringwald's review of the experiments that are currently going on at DAISY in Hamburg, who have taken this quite seriously. Baby AXO is not yet constructed, but the ALPS experiment is now being installed in the Hera tunnel. Earlier, they had done a Pathfinder. So they are actually going to be exploring some of this parameter space. But meanwhile, Konstantin had been exploring with my colleague Gianluca Gregory and others in his laser laboratory astrophysics group, the possibility of detecting axions with high-powered lasers. And they thought of several ideas, which I in the citations of here. In the event, we settled on the idea that actually had been proposed by Wilfried Buchmuller and Hugovin, which was to actually use, rather than a large magnet, which are expensive, a little crystal, because a little crystal has actually a very strong electric field in the lattice, and the equivalent magnetic field can be of order 1,000 Tesla. And although the crystal is very small, it's only a few hundred microns, the product of the equivalent magnetic field and the length through which the light will traverse is comparable, competitive with the much bigger experiments that have huge expensive magnets. So the idea is that you send a photon, in this case from a free electron laser, into the crystal where it undergoes internal reflection. And then you have another crystal which is aligned parallel to it. And then this axion can only go between the two because there is a shield between the two crystals. So photons cannot penetrate it, only an axion can. And if an axion does go through and converts back into a photon, you can then detect it at the end of this pipe with a X-ray detector. Right? They use something called a Jungfrau. This is an actual experimental setup which ran at the X-ray electron laser in Hamburg, which is in fact operated by DAISY. It is fed by electron beam from DAISY. And you can see here that subject to these Bragg condition that is outlined here, you would be sensitive to axion masses that obey this. And if you tune the crystal angle away from this exact Bragg limit, then you'd be sensitive to axion masses which are indicated here as these vertical red lines. So you're ruling out the entire pink region of axion mass as a function of the coupling, and also these individual discrete lines. And the reason why the experimentalists who are shown here in this picture, that in the middle there is Gianluca, and they are confident that no axions came through, because if they did, they would be along the same direction as the initial X-ray laser beam, which is this blue spot in the middle. And although they did see some photons, these were not in the same direction. These are clearly scattered photons because of the backgrounds. And there is considerable background. So for example, the dark count itself, which is this black line here, that is what the detector sees as a function of the photon energy from various backgrounds. But what you're looking for is a little excess due to the axion conversion, which is in fact not seen. And on the strength of that, you can put a bound on the axion mass. There are many issues to do with the detector as to what axion masses you can probe. But basically, for the purposes of this talk, I just want to point out that the probability of the axion photon emission goes as the square of G. And therefore, you would need to increase the sensitivity quite a lot by about a factor of 10,000 to go down in GA gamma gamma from where we are presently down to the level where you are touching the QCD axion line. But the experimentalists think they can do that. Okay, so I see that I've exhausted my time, so let me come to the conclusion. QCD axion models which have the number of quarks charged under the Pechogin symmetry more than one, they have a problem with domain wall formation in the post-inflationary scenario. And this network is unacceptable cosmologically, as has been known for a long time. But you can get rid of them by effects which are, in fact, quite natural, violation of global symmetries by Planck scale effects. And the wall network will then decay away. But if you tilt the domain wall network in order to make it disappear, then you also regenerate electric dipole moment of the neutron, and that won't make our experimentalist colleagues happy because they've ruled that out. So if you put the two together, then there is no getting away from the conclusion that the axion mass has to be more than 11 milli-electron volts in this DFSE model. And therefore, you need experiments which are targeting this mass range. I'm very happy that our laser colleagues have got interested in this problem, and I hope others will too. We are hoping now to do a similar experiment at the free electron laser at SLAC. I also want to mention in conclusion that these axions are of this kind of mass are supposed to have been excluded by supernova 87A. But as some of you may know, those arguments have come under renewed scrutiny because there are lots of astrophysical effects in the supernova that lead to uncertainties in the conclusion. And in fact, recently, these papers you can look at argue that there are actually observations of stellar cooling which cannot be accounted for by conventional processes. And if you ascribe that to the uh, energy loss due to axions, then the mass range that is implicated is in fact around 10 millielectron, 10 to 100 millielectron volts. So that is very intriguing. And it looks like there is more than one way then to try to detect axions of that mass if they indeed exist and are responsible for solving both the strong CP problem of QCD, which is urgent, and also for providing us a very natural candidate for dark matter. Thank you. I'll stop there.
Okay, thank you, Professor, for this nice talk. So, if the audience has any question, please unmute yourself and ask.
While we are waiting, I wanted to say is, if you are interested in this, you might like to look at that SciPost webpage to see what the referees said and what we answered to them. Go ahead.
I have a question.
Yeah. Hi, Alzad.
So I have not understood around the middle of the talk. You say, you have an equation that you cannot solve numerically. So there is a trick, but the trick seems solving a different equation. So I don't understand.
That's correct. But the different equation does not do anything very bad. It still conserves energy and momentum. Okay. And actually, that is pretty not relevant anymore because, Alessandro, since that time, that was 1997, computers are now so much bigger and cheaper that people are in fact able to encompass with the dynamical range now the real equation, which has got a square in front of the potential. And so they can accommodate the sharply increasing barrier height. Because their grid size now is not 128 cube, it is 100,000, 1,000 cube. Okay, so it's much, much bigger.
Okay.
So that was just for historical interest.
Okay.
Thank you.
Yeah. Thank you.
Hello.
Hello.
Yeah, may I ask a very naive question?
Please.
Yeah, so you are saying that the symmetry, the ZN symmetry is broken by some tilt. So if this symmetry is broken, so how does this domain wall form at the first place? Because it seems like there is no ZN symmetry. So during the spontaneous symmetry breaking, so all patches of universe would prefer to go the lowest possible uh, uh, vacuum, like lowest energy vacuum, so that it can uh, it can exert the highest amount of free energy or something like that.
No, but the symmetry is not being broken explicitly in the Lagrangian, right?
Okay.
So the Axion we are discussing the formation of domain walls in the context of some model for the Axion, right? In that model, let me go back to the slide that is relevant so you can see what is going on. I think schematically I sort of showed that. Sorry, you probably can't. Can you see my slides now, or shall I reconnect that?
No, I can.
You can't see. Okay, let me go back to sharing. Where are we? Yes, here. Okay, so basically the Pechequin symmetry is broken at some high scale, right?
Mm-hmm.
But the discrete symmetry that I'm talking about only gets broken when you get down to the point where the axion gets a mass.
Yes.
Right? So therefore, you cannot, it is not the case that this is pre-broken and therefore there is only one choice for the vacuum to be selected as
Okay,
you.
okay, I get your point. Thank you.
Okay? Right. So if you look at this potential, then it will become clear.
Yeah, yeah.
All right. Thank you. Are there other questions?
Yeah, there is a one question from audience Pratik. Is there any theoretical lower bound on QCD action mass, not necessarily dark matter, other than non-observation from astrophysical or cosmological observations?
A theoretical lower bound on the QCD action mass is an upper bound on the Pechequin scale. So I don't know. I suppose you could hand wave and argue that the Planck mass is an upper bound on the Pechequin scale. So in that sense, there is a lower bound on the axial mass. But I don't have any good reason to say that. I'm just saying that that's the first thing one would think of. But that is pretty another way of saying that you cannot have any global symmetries that are not violated by quantum gravity effects. But that is actually a somewhat, well, I'm not going to make that claim. That claim has been made by others. And sometimes people ask, why is it that has to be the case? I'm agnostic about it, but maybe one of the people on the call can answer that. Alessandro, do you have any view about that?
Sorry, I got distracted there.
Okay, the question was, is there a lower bound of the axion from theoretical grounds? And I said the only thing I can think of is that the Pechoquin scale really can't be higher than the Planck scale. But I say that in a purely hand-waving manner. I have no good reason to assert that. Can one say that more strongly?
Sorry, so the issue is about what? About gravity?
No, the issue is about, can one actually say that there is a, issue is about gravity as to whether you could have a global symmetry like Pechequin not violated by quantum gravity, essentially.
There are very special models where operators have very big dimension.
Right, exactly. You have to suppress all the lower dimensions up to some very high order.
Mhm.
Right. Which seems unnatural, but I mean, that's the only thing I can say in answer to that. Pratik, are you happy with that? Well, I hope he is. He has not said anything.
Is there any other questions?
So I have a question.
Please.
The experiment, this free electron laser experiment that you mentioned,
Yes.
that is very similar to light shining through wall type of experiment.
It is a light shining through walls experiment.
Correct. So
Yeah,
it is
except that we are
suppressed
not in the light shining
yes.
through wall experiment. They use magnets. We are using
magnetic field. You
Yeah.
are using electric field. Yeah, that's
Correct,
right.
correct.
So it is suppressed by probability square.
Yes, it's exactly the same
Otherwise,
argument.
yes,
It's
that's
the
right.
same. The probability goes as the square of the coupling.
Correct. So
Right.
can one
But that
also
makes it
think
totally
about-
model independent because you're creating it by the same process as you are destroying it.
Correct. Yes,
Yeah.
that's right. I was just thinking if one can also explore this region of action mass using the polarization property of the studying the polarization property of the laser light, because that will be changed, right? Because of this mixing of action and the photon, the rotation plane of polarization or things like that.
Yeah,
where you have
sorry,
only
before
one.
answering that, I just want to point out that one of the proposals that was made by Bayer et al. Was a
Yeah.
experiment where you don't have the square, but only one factor of gamma
Correct,
gamma
yeah.
by
Yeah, I
as
can
is shown here. But that actually is pretty harder to do because you'll have so much scattered light that you can't. It'll be well for practical reasons that experiment might prove harder to do because in all cases you really want to create the axion but from a photon, pass it through a wall and have it reconvert to a photon on the other side. Now, with regard to polarization, that's an interesting suggestion. We haven't thought about it. I will pass it on to the people who proposed this idea to see if they can do anything with it. But yes, thank you for that thought. These things are worth thinking about.
Thank you.
Pratik said yes, and he said thank you. Okay.
Okay.
Is there any other questions?
Yeah.
You can ask.
Inflation scale can't be below travel scale.
Sorry, I'm not getting any of that. Can you type in your question into the chat box, please? Or did anybody catch the question? Hello?
I did not understand it
Yeah.
clearly.
There's too much of an echo. So okay, nobody's typing anything. Okay, please try speaking again, and I'll try to.
He typed it, Professor. He typed it.
He typed it. Oh yes, he said that the inflation scale cannot be below the electroweak scale due to the formation of baryons. Oh, it's very simple. If you, I mean, when you have inflation, it gets rid of everything in the universe, and so if you have, if you want to make the baryon asymmetry, which is after all essential, otherwise you won't be here discussing anything, then it has to be after inflation. So inflationary scale. Now, then the question is that what is the scale of baryogenesis? And most of us would be more comfortable if it was, we would think it is basically the electroweak scale. It can't really be much below it. I mean, there are, of course, mechanisms like Affleck-Dine, which are not related to the electroweak scale at all. But in order to do Affleck-Dine baryogenesis below the electroweak scale, you are really asking for a lot. Because then you don't really have a calculable program. Whereas in the electric theory, because there are baryon number or fermion number in general is unsuppressed at temperatures above the electric scale, you have attractive mechanisms like leptogenesis, etc. It doesn't matter what you create the asymmetry in, it will be shared between all doublets of SU2. And so that's kind of more attractive. But I don't have a theorem that says inflation can't be below the electric scale. It's just that it would have to be pretty contrived. Okay.
Okay. Okay. So, is there any other question?
May I ask another question?
Please.
Yeah.
You said that this Pecci-Quinn scale should be less than around 10 to the power 8 GB. So the string tension will be quite low in this case. So do you think they will assume some kind of scaling regime or something like that? And you can estimate the number of domain wall per horizon in this situation?
Well, those simulations are not directly tied to the tension. They are generic. The scaling regime is reached after a certain. So the only scale in the problem when you do the cosmological evolution is the Hubble parameter, the Hubble scale. There's no other. And the string tension is indeed what decides the width of the walls. So basically,
Yes.
you'll have fat walls or fat strings if the scale is small. But there is always a large hierarchy between the Hubble rate and the string scale. So you are right that if the two become comparable, then the simulation will have to take that into account, right? But generically we are thinking of extremely compact objects whipping around in a huge space.
I'm asking what will be the effect of some kind of scattering of the string with some external plasma with string having such a low string tension, like
When
on
you
a
say
bomb
low,
scatter.
but it is, the inverse of 5 × 10⁸ GeV is still a pretty small number. So it is still a pretty compact object, right? And so it is true that if these strings or domain walls become sort of large, then they can have all kinds of interesting effects. So for example, I looked at what would happen in the core of the domain wall, where, well, for example, what effect they might have on nucleosynthesis, right? Neutron-proton conversions are, of course, affected if they happen to be in a symmetric vacuum. Unfortunately, the thickness, the actual volume of space that is occupied by the core of these topological defects is absolutely tiny. So generically, they have no effect. But in principle, if they were as massive, as thick, or as extended as the size of the box that you're doing the simulation in, which is typically the Hubble radius, then sure, then you would have to take those size effects into account. We're quite far from that situation now. But it's an interesting thing to consider because actually I'm not aware of in the condensed matter systems whether one might have such a situation where you see topological defects. They even see textures which are sort of comparable to the size of the bottle or whatever it is they've got it in. So my answer is I don't think simulations have been done which consider that possibility, but it would be an interesting problem to study. It's not relevant to the present case because these are still pretty compact objects.
Thank you.
Sir, any more questions? If there is no other questions, let us thank the speaker for this interesting topic. Thank you, Professor, for joining us.
Thank you very much for having me, and I hope more of you will post your submit your papers to SciPost and also help in referring and so forth. Thank you very much.
Thank you.
Bye then.